So we're going to identify excluded values of rational functions today and graph some very basic ones. One of the things that's really interesting to me as a teacher is that my classes all end up at the same place, really close to it at the same time. We're talking about this exact same thing in Algebra C right now. And we're going to talk about some of the same use the exact wording and everything I did during first hour. A rational function is a function whose rule is a quotient of polynomials in which the denominator has a degree of at least 1. In other words, there must be a variable in the denominator. The inverse variations you studied in the previous lesson are a special type of rational function. Okay? So here's some examples of rational functions. Right here, we have variables in the denominator, and these here are just linear functions. All right, a rational function has some type of variable in the denominator. Okay. For any function involving x and y, an excluded value is any value that makes the function undefined. For a rational function, the excluded value is any value that makes the denominator equal to 0. So we can't divide by 0, right? Okay. We've already talked about these, haven't we? We've talked about when things are undefined. No, we haven't. We're just doing it now. Okay. I'm getting my Algebra C stuff mixed up. Okay. So when we talk about excluded values, we're talking about what makes the denominator equal to 0 because we can't divide by 0. So that's the first thing we're going to do is what makes a function equal, or what makes it undefined. So we need to find excluded values then where the denominator is going to be equal to 0. So letter A, y equals 2 over x. What number would make that denominator equal to 0? 2? So what's 2 over 2? 1. Nope, guess not. Good try. How about 0? If I put 0 in there for x, would that make the denominator equal to 0? Yes. Okay. So, what's that? Why couldn't you use 0? We're talking about what makes the denominator equal to 0, because when the denominator is equal to 0, it's undefined. Okay. So that means that 0 would be an excluded value. In other words, a value that could not be used in our domain. Okay. So what we do is we would set the denominator equal to 0. So if I say x equals 0, then x equals 0, doesn't it? Okay. So the excluded value in this case is 0. Letter B. So we want to take the denominator, x minus 2, set it equal to 0. And then solve for x. So when we solve for x, then we add 2 to both sides. We get x equals 2. So the number 2 is going to make the denominator equal to 0, so that would be our excluded value. And we're not saying x equals 2, we're just saying the excluded value is the number 2, because that's where the denominator equals 0. So you remember finding zeros, right? When we were factoring it like that, we found zeros. We had to do that on that test, okay? So we're doing that same thing, except our focus is on the denominator. What makes the denominator equal to 0? So for these three problems here, okay, most rational functions are what we call discontinuous functions, which means their graphs contain one or more jumps, breaks, or holes in it. This occurs as an excluded value. You see my note here to remind me to give you the handout I gave you? Okay, it's a good thing I looked at that earlier today because I'd forgotten. Okay. One place that a graph of a rational function is discontinuous is at an asymptote. Did we talk about asymptotes already? Okay. All right. Asymptotes are lines on a graph, lines that where the graph gets closer and closer to it, but doesn't actually touch it. Okay. So the graph here of 1 over x, the rational function that we've looked at, it gets closer and closer to the y-axis here and here, and it gets closer and closer to the x-axis here and here. But it never actually touches them. They never actually become 0, because if they became 0, we'd have 0 in the denominator, and we can't divide by 0. So these two lines, the x-axis here and the y-axis, are asymptotes. Graph gets closer and closer to it, but never touches it. It's also a spot where there is horizontally, that's where excluded values are going to be where the asymptote is. Okay. Vertical asymptotes, we have vertical and horizontal asymptotes. Vertical asymptotes will occur at excluded values. So when we look at this graph, we can't put 0 in for x. That would be an excluded value. So we would say there's a vertical asymptote at x equals 0. And there's also a horizontal asymptote at y equals 0. So those are the places where there are gaps in the domain. Okay? Our domain, as we go from left to right, all right, we have values for x all the way till we get to the y-axis. It's not there. There's an asymptote there. There's a break in the graph there. Vertically, all right, as we go from negative infinity up to positive infinity, so if we go up, we can see there's a break in the graph vertically. So that's where we have a horizontal asymptote. Vertical asymptotes, or vertical lines, are written in the form x equals b, and horizontal lines are written in the form y equals c. So for instance, look at this graph here. We have the graph of 1 over x minus 3 plus 2. Notice that the graph here, the red lines, looks just like the parent function 1 over x. Y equals 1 over x. Has the same general shape. The only difference is that this vertical asymptote here at x equals 3, instead of it being at 0, it's at x equals 3. So it's been moved to the right 3 units. And the graph has been moved up 2 units. So instead of the horizontal asymptote being the x-axis, y equals 0, it's been moved up to y equals 2. So basically all we've done is take this graph here, move it 3 to the right, and 2 up. So what we're doing is we're doing translations, horizontal and vertical translations. Things we did with that we'll do with lines that we've done before. Okay. All right. How many of you remember doing translations? Okay. Moving stuff vertically and horizontally. Okay. All right. And so they come with this formula here, and this is on that handout I gave you. Okay. This sheet right here. All right. A rational function in this form, y equals a over x minus b plus c. Has a vertical asymptote at x equals b and a horizontal asymptote at y equals c. So for instance, The graph of y equals 2 over x has a vertical asymptote x equals 0 because that's where the excluded value is in the denominator, and a horizontal asymptote of y equals 0. The values of b and c. In this other example, y equals 1 over x plus 2, that quantity plus 4. Our value of b is negative 2. The value of c is positive 4. So we'd have a vertical asymptote at x equals negative 2 and a horizontal asymptote at y equals 4. Notice that it's x plus 2 here. Our excluded value would be negative 2 because that's what makes the denominator equal to 0. So we would say our vertical asymptote is x equals negative 2. Right? We're looking for what makes it equal to 0, the denominator. So they want us to identify the asymptotes here. And you can use abbreviations. You can use VA for vertical asymptote if you want, and HA for horizontal asymptote. But what must happen is your vertical asymptote is always going to be x equals. Your horizontal is always going to be y equals. They are lines. They're not just numbers, they're lines. So you have to write them as lines. So we need to identify B and C. Dylan, what's the value of B in this problem? Yep. 7? Okay. So if I put 7 in here for x, I'm going to get 0, right? Okay, negative 7. All right, that's better. The value of B is an excluded value. Okay, so what makes the denominator equal to 0 is our value for B. All right, how about C? What's the value of C here then? Right? Let's see, what's the value of C? 0. Okay, if there's nothing there, it's 0. So my vertical asymptote would be x equals negative 7. My horizontal asymptote, y equals 0. So we want to identify B and C, and those are going to tell us the numbers for the horizontal asymptote and the vertical asymptote. Okay? It's always got to be x equals and y equals. All right, you okay, Matt? Oops. Okay, we need to find B and C. So Natalie, what's the value of B in this case? 3 over 2. Very good. And would you tell us how you got that? Okay. Good. So you found the excluded value, right? Set the denominator equal to 0 and solve. Very good. Okay. All right, and the value of C in this case is what then? 8. Okay. So my vertical asymptote is x equals 3 over 2, and the horizontal y equals 8. Y equals 1 over x minus b plus c. All right, now we're going to use that information then to do graphs. So we're going to graph these rational functions, or this one, by using asymptotes. And this is where we got the graph paper out so we can make our lines exact. And so we need to find the values of B and C so we can tell where the vertical and horizontal asymptotes are going to be. Mitchell, what's the value for B? 3. Good. And Cheyenne, how about the value of C? 0. Yep. Right. Plus 0. There's nothing there. Now, so here's what we're going to do. So just give me a second here, and I'll show you what we're going to do. Okay, so we have our normal, our parent function here, looks like this. Right? There's the parent function. In purple, we have y equals 1 over x. That's our parent function. So what does this do